Okay, this is section 12.1, day 2. We're looking at an introduction to limits. So we're starting in a little bit more with our examples from the discussion we started on day 1. So the first example that we're going to do, I want you to go ahead and pause the video so you can draw the picture. It's really important that you get the pictures to go with these to look at what's happening. There's lots of extra room in this section, so feel free to jot it down wherever you need to. So we have this graph, and there's some places of discontinuity. Excuse me, and some like a jump discontinuity, a point discontinuity. We have a lot of different things going on in this function called f of x. So we're going to use the graph to determine whether the value of the quantity that we're looking at exists or not. So we're going to look at some function values and some limits. All right, so for the first one, it says, what's the value of the function at 0, f of 0? Remember, when you say that, that just means like the x value is 0. So I'm going to look at the graph at x equals 0. So I'm looking on the y-axis. The location where the point is actually filled in is right at 1. So the value of the function there is equal to 1. So that's where the dot is, right? That's where it's filled in. So the value of f of x is 1. Now, the interesting thing, though, to look at is what would the limit be as x approaches 0 of this function f of x? And here's where the interesting thing happens. Coming in from the right-hand side, so looking at x values as they get smaller and smaller and closer to 0, the function value itself, if you just trace on the line, is getting closer and closer and closer to that value of positive 1. So we would say the limit as x is approaching 0 from the right-hand side, so we're going to call that a plus, of the function would be equal to, or maybe I'll just say it this way. The function of f of x approaches 1 as x approaches 0 from the right. So we'll just kind of make it like our sentences when we did end behavior and left and right and all that before. So the value of the function is getting closer and closer to 1 as x approaches 0 from the right. Now here's the problem, though. As we approach 0 from the left-hand side, so as the x's approach 0 from the left, if we trace along the function, the value of the function is actually getting closer and closer to that open circle, which happens to be happening at positive 3. So the function f of x approaches 3 as x approaches 0 from the left-hand side, we say, when we say 0 with a little negative, meaning coming from the left-hand side. So here's our discontinuity, our issue. It's approaching a different number from each side. So if the value of the function isn't closing in on the same value from either side, the limit does not exist. So when we look at that one, this would be a does not exist, a DNE, because we have what's happening at this graph is a jump discontinuity, we call that. It's jumping from one value to another one. So a jump discontinuity is going to make your limit not exist. So at places of discontinuity on the graph, we have to be really careful when we look at limits because they're not necessarily going to exist. So because it approached a different value from each side, the limit does not exist. All right, so I'm going to move this from, oops, got to get my circles back in here. So we have that. All right, so close there, open there. All right, so let's take a look at the next one. The value of the function at 2. So we're going to look at a different location. So the value function when x is 2 is happening right here. So it looks like 2, and we go down. It's an open circle. It doesn't exist. There's no filled in dot on our graph when x equals 2. There's an open circle there, okay? But can the limit exist even though it's discontinuous there? So we're going to look at the limit as x approaches 2. So let's see what happens. So as we get closer and closer to 2 from the right, if I trace along the graph, it looks like this is getting closer and closer to this value, which was marked at -1. So it looks like the limit, or the flat value of the function, we'll say. So the function looks like it's approaching -1 as x approaches 2 from the right-hand side. Well, as we approach 2, so from the left-hand side, so as we get closer and closer to the value of 2 coming this way, if I trace on the graph, it sure looks like I'm closing in on that same location. So the function itself, if you trace on it, looks like it's getting closer to -1 as x approaches 2 from the left, so when it's coming from the left-hand side. So they're closing in on the same number. Now, it is totally true that the value of the function is not continuous there, right? It's discontinuous. It's an open circle, point discontinuity. But the actual value of the limit does exist because the value of the function approaches the same number from both sides. So the value of the limit is actually going towards -1. So the limit can exist even when it's discontinuous because this one was a point discontinuity. So the type of discontinuity really does matter. What's happening on the graph. So it's point, let's see if I can spell here, discontinuity. Trying to talk and spell at the same time. There we go. So a point discontinuity is going to allow you to still have a limit even when the value of the function doesn't exist. So being able to identify what's happening on a graph is a really big part of what our discussion is going to look like over the course of the next few weeks here and what you'll start talking about in calculus as well. All right, so let's try another one to show an example of a limit that does not exist. So we want to see what something could look like. So again, this is going to be an additional one, and so please take a second to go ahead and jot down what you need to, and then you can go ahead and start the video again. So this is a piecewise function. So if you remember doing those earlier this year, you just have different rules that define different portions of your domain. So for all the x's that are less than or equal to 2, we have this linear equation. That's our first piece of -2x. And then for the second part, we have, it looks like a parabola equation for all the x's that are greater than 2. So our first kind of, I guess, job here is to graph those two pieces. So I'm going to graph the equation y equals -2x for all the x's that are less than or equal to 2. So I for sure need to put in that domain value of 2, and then I need to do some x's that are less than 2, whatever you need to do. Sometimes it's nice to fill in a table so we can put in those values and have some numbers that work well. And then we need to talk about, is it going to be open or closed at this domain value of 2, -4? Well, it's equal to, so that means it's a closed or included location. So for that part of the graph, we're going to have a closed circle at 2, -4. And then we're going to have that linear equation going back. So 1, -2, 0, 0. You could also use the slope, up 2, back 1, up 2, back 1. That's totally fine. That would be that first part of the graph, or the first piece. The second piece of the graph is this quadratic equation, so parabola, which is that U-shaped kind of graph. And that one's going to start at the x's being 2 as well. Because it's not equal to, that's going to be an open circle, but I still need to put that domain value in. So when I put in 0, or put in 2 for that value, we would get, let's see here, 4 minus 6 plus 1 looks like -3. And then we need some values that are bigger, so I'm just going to put in a couple more. So go ahead and plug those numbers in. Pause the video if you need to. Plug in 3 for x in that quadratic. Plug in 4, and we can see our values. We just need to get enough points so we can see what the shape is doing. So at the point 2, -3, we're going to have an open circle because it's not included, so no equal to here. And then we've got 3, -2. We'll go ahead and graph that point. And then we have the point 4, 1. So I'll do my two pieces here in different colors. All right, now I want you to take a look and see where would limits exist and where wouldn't they? So the places that we need to worry about are the places where our graph is discontinuous. So the point that I would be worried about is right down here. So at the x value of 2, which is where your domain is looking to change, if I ask you what is the limit as x approaches 2 of this function f of x, what would we have to say? Well, the limit looks like it's approaching positive or -3 from the right-hand side. So the function itself is approaching -3 as x approaches 2 from the right. But on the other side, if I trace along here, it looks like it's going towards -4. So the function is approaching -4 as x approaches 2 from the left-hand side. So we'd say 2 with a little minus there. So there's our disconnect. It's approaching a different number on each side. We have what we call a jump, again, discontinuity. So the limit would not exist at that location. So we really have to take a look at what's happening on the graph to be able to tell. And once we know if a limit exists or not, we're going to be able to do a lot of things. And if we know what the graphs look like kind of beforehand, we can think about what that means, and we don't have to do quite as much work. But we have to think about continuous versus discontinuous. Where are the functions having these breaks, and does that affect what happens for the limits? All right, so we have some things we know to be true then about properties of limits and how we can calculate them. So on on things that are continuous and everything works easily, we know that these are always going to be true. So we're going to go through some of these properties of limits. So let's take a look at how they're writing them out. C is just a real number. It's the number that you're approaching. So these, what we call just direct limits. And B is the number that they're going to use too to represent just if it's a constant, so they have a value in there. And N is a positive integer. They're using that for exponents, so we always have positive integer exponents. So let's talk through each of these properties and see if this makes sense to you. The first property I kind of call the constant property. So this would be the limit as x approaches c of a constant, meaning like just a number. So I'm going to give you an example over here. So like the limit as x approaches 7 of the number 3. So remember, this is like y equals 3, and y equals 3 would just be a horizontal line at 3. Well, it doesn't matter where you are in a horizontal line at 3, no matter what, you're always going to be approaching 3. So it stays the same. In other words, the value of a constant is just itself when we look at that limit. It's going to be the same. It doesn't change. That's what constant means. The next one is called the identity function. Thinking about like a linear equation. So this is an identity. We talked about like that y equals x, that would be like we talked about back in our families of graphs. So the limit as x approaches c of the identity function. Well, the identity is the graph y equals x. So that's this graph. So 1, 1, 2, 2, 3, 3. So the limit as you get close to 1 would just be 1, because in this equation, whatever y is, x is 2. The limit as x gets closer to 2 is going to be 2. In other words, the limit as x approaches c of x is always just going to be whatever that c value is. The identity function, that value is always the same. That's what identity means. All right, now what if we have something raised to a power? So like it's kind of like the identity function, but then raised to a power for number 3. So they call this the power one. That would be like x squared or x cubed or x to the 4th. All of those would be examples of power equations. Well, whatever number you're putting in, whatever that constant is, that's going to be the value of your function there. So if we're looking at what's the value as x approaches 2, it's going to be whatever 2 to the n is, because that's a continuous function. We're just plugging in the 2 for x. These are called direct substitution, because we can just substitute the value in and figure it out, because the functions are continuous. So we'll take a look at that when we do some graphs and talk about those examples. All right, so the next one is the root, same idea. So this is the radical version, we call that radical, because it's a root. So if you're doing the same sort of thing, it's a continuous function, like a square root, a cube root, fourth root, whatever it might be. The value of the limit is going to be the same as the value of the function. So that would be the nth root of whatever that constant is. So on these direct substitutions, if we have continuous functions, the value of the limit is equal to the value of the function at that location. And that's a really important kind of statement to be talking about. So we want to make sure that we, go back to that, the value of the limit is equal to the value of the function, because they're continuous at these locations, because it's a continuous function. There's no breaks, nothing that we have to worry about. So the value of the limit equals the value of the function. Another thing to kind of think about, then we'll go through and do some examples with that, is you can do operations with these limits then. So we can take two limits that if we know values for them and put them together, which is really cool, or do scalar multiplication, all the different things that you'd assume you'd be able to. So if you have two functions and looking at their limits, so limit as x approaches the same number of one function and then the other, we can do all sorts of things. So here's the first one. Scalar multiplication means you can multiply a number times a function, and the answer will be that number times the limit. Then you're multiplying just by whatever that value is. So it'd be b times whatever the value of the limit is. So they're saying L, this L is supposed to stand for whatever the limit was. So if you have b times the function, then it's just going to be b times L. If you add or subtract two limits, that means you take whatever the value of the first limit is and either add or subtract the limit of the second one. So you can just add or subtract those values. You can put limits together. So you can do operations with limits, in other words. You could multiply them together as well. So whatever the limit is of the first one times the limit of the second. You can divide them. So L divided by K. Just be aware the K can't be 0, right? Because we can't divide by 0. And you can also take limits to powers. So if you have the value of a limit and you're raising it to a power, it's just whatever the limit is then raised to that power. So we can do operations with these things as well. So we're going to talk about this idea of like the direct substitution, finding a limit directly by just plugging the value in. And we'll take a look at the graphs as well so we can see what we mean. All right, so let's try a couple so we can get into this. We have a lot of properties, but let's see if we can do one. So we have the limit as x approaches 4 of the function 3x squared. Okay, so the first thing I want you to think about is the function 3x squared for a second. So y equals 3x squared. So that's a parabola. It's degree 2, and it is a continuous function. If I wanted to graph what that picture was, so go ahead and pause the video for a second. Go ahead and type that into your y equals, just so you have a visual. So 3x squared, or you can just type it and listen here. Oops, that's not squared. There we go. And I'm going to go ahead and graph on a regular window. That's a continuous function. There are no breaks in this graph. So what I'm asking you to find is as x gets closer and closer to 4, what would the value of the function be? So here's what I'm going to have you do. Go ahead and hit trace, just like we were doing before. And I want you to trace on your graph until the x value gets pretty close to 4. Now we're going to go off the screen here a little bit, but you can still see the x's changing on the bottom. As x gets closer and closer to 4, sure looks like my value of y is getting closer and closer to right about 50, it looks like. And if you want to change your window just so you can see that a little bit better, I'll put it up to 60 just so we can see that. If I trace, oops, I changed the wrong one. I don't need that to be 60. I need my y max to be 60. And if you look at the picture then and do the trace, you can really see it happening pretty clearly where that output's going to be. So I can do the same thing as x gets closer and closer to 4. Oops, went a little bit too far. It looks like it's going to be pretty close to 50. And I can come from the other end, so from above and come down, and it's still going towards 50 because it's continuous there. So this graph is continuous everywhere, because the domain is all real numbers. It's a parabola, right? So all reals, if you want to say it that way, or negative infinity to infinity. So that means it's continuous everywhere, so it's definitely continuous at 4. What that tells me is to evaluate the limit, I can do direct substitution. So the value of the function at 4, so like f of 4, is going to be the same as the limit at x equals 4, or as it approaches x equals 4. So let's just do that direct substitution. So 4 squared, first of all, that'd be 16. And then times 3, which would be about 48. All right, so let's go back to our graph. We said it was somewhere in that ballpark. So when I was tracing, and we do our 3x squared, as x gets closer and closer to 4, it's kind of jumping over. So we got 43, 46. When we're a little bit bigger, it's 50. When we're a little bit lower, it was 46. So yeah, kind of in the middle there. It looks like that's a pretty reasonable answer. Now, it's going to be a little bit harder to tell from just the trace, because we said like a ballpark of 50, but somewhere real close to that. Our direct substitution is showing 40. Remember, you could always go to your table, right? So we could look at our table and find the actual value of the function, and there it is at x equals 4. There's our 48. That's direct substitution too. So we can see that, yeah, that kind of makes sense. That's where that value is going to be. So the value of the function equals the value of the limit when it's continuous. So it's a parabola. We know that that value is going to be 48. So a lot of people write just L equals for these after they write kind of that original. So you could say L equals 48, or you have your limit sentence. We need to keep track of those. All right, so we're going to add some in just to practice a little bit and see how we're doing here. So we're going to do a bunch of these just to make sure they make sense. So we'll talk about a whole bunch of these so we can practice those different functions. So go ahead and jot them down as we go. Pause if you need to. So the limit is x approaches 3 of 1/4. 1/4 is a constant. That is the function y equals a fourth. That means if you graph it, you're going to have a horizontal line going across at 1/4. So what's the limit as x approaches 3? Well, at an x value of 3, the value function is just going to be 1/4, and it's always a fourth. As you get closer and closer to 3, never changes. That's the whole idea of a constant. So the limit of the constant is equal to the value of the function. It's just going to be a fourth. It's constant. It's continuous. X cubed. We remember what x cubed looks like, so you can go ahead and graph it on your calculator. But x to the third, they want the limit as x approaches 3. X to the third, again, is continuous. It's a continuous function. We have a domain of all real numbers. We can put in anything we want. So the value as x approaches 3 as we get closer and closer to 3 on both sides, is going to be closing in on the same value, and it's whatever that function is evaluated at 3. It's a constant, or it's a continuous function, so it's going to be direct substitution. So the limit would be equal to 27. So if I look at the graph of that function, the value of the function is equal to the value of the limit because it's continuous there. All right, let's take a look at the next one, a little bit more complicated. You can't necessarily recognize this as limit as x approaches pi of cosine of x over x. It's not a parabola, it's not a polynomial, it's just a rational function. It's got a, well, actually not even rational, it's just a ratio of two different functions. So is it continuous at each of those places? In other words, can I just plug these numbers in? So cosine of pi divided by pi. Well, that's a completely legitimate thing to be able to simplify. So the cosine of pi is -1. Pi is just itself, so this would be -1 over pi. So when I look at that value, I can actually evaluate direct substitution. It's continuous there. I can plug the values in. If it was discontinuous, I would not be able to substitute anything in, and I would know I'm going to have to deal with something else. All right, let's try some more. All right, next one, letter D. Limit as x approaches 12 of the square root of x. So go ahead and graph it on your calculator. Square root of x looks like this. As we get closer and closer to 12 on each side for x, we're going to be closing in on whatever point that is on either side. So it's a continuous function there. The domain is all reals that are greater than 0. Remember, we can't take the square root of a negative number, but it's definitely defined at 12. So the limit would be equal to whatever the square root of 12 is. Now, you could simplify that if you wanted, so 2 root 3, but that's an exact answer. You can trace on your graph and see that it gets closer and closer to whatever the square root of 12 is. So we can do roots. That's another one of our properties. All right, let's try the next one. Limit is x approaches pi of x times tangent of x. So let's see if this is something we can do with direct substitution. This isn't a function we necessarily recognize this product, but let's see if we can do direct substitution. So we're going to substitute in pi for x. All right, so you need your special values here. Tangent of pi. Tangent of pi, slope at pi would be 0, so the limit would be 0. So if you graph this and look at what happens as you get closer and closer to pi, you're going to get closer and closer to 0. All right, last one, another parabola here. So it's continuous. It's opening down. We got all sorts of different things going on here. They want to find out the value as x approaches 3. Because this is a continuous function, we know it's defined there. We can do direct substitution, and we can just solve. So just be careful with your values here. So it looks like the limit would be 4. So if it's helpful for you, graph it first so you can look at it. But direct substitution for limits really means the value of the function equals the value of the limit, which is what we're talking about here. So if it's a polynomial, for sure, we know that if we're taking a limit, the value of the limit's also always going to be equal to the value of the function at that point. So that just is what we're just saying. So the value of the limit is always going to be equal to the value of the function at that c. So at c. So the way they're saying it is polynomial p of c. So polynomials are things like x squared, x cubed, x to the fourth, the things that we know really well because those are continuous graphs. And that's why this works. There's no breaks, no holes. They're just continuous. Rational functions, same kind of idea. The value of the limit of the rational function is given by whatever that ratio is. So you have to actually do that division, but that's the same kind of thing. If it's continuous there, that means where it's not equal to 0, then it's going to be defined and the value will be equal to the value of that function at c, which basically means whatever the numerator is evaluated at c and whatever the denominator is evaluated at c. In other words, you can do a direct substitution. If it's defined there, and that's the key, the limit is going to be equal to the value of the function if it's defined at c. So it has to be in the domain of the function. So just be careful about that. If C is a place where it's discontinuous, so we got to check for discontinuities, right? We need to make sure that it's a place where it's continuous. So we need to check that. So that Q of C, we got to double check and see what makes that 0. But if it's defined at C, then the value of the function again at C would be equal to the value, oh, I wrote value twice up here. Sorry about that. Value of the limit. Probably like, what is she doing? So rational functions, polynomial functions, things that we know how they behave, it's defined at that value. If it's continuous, we know the value of the function is going to equal the limit. If it's discontinuous, we just have to check and see what's going on. If it's like that piecewise graph we did and there's a jump, the limit's not going to exist there. But if it's just a whole, a point discontinuity, then we're going to be okay. So we really do have to kind of take it on a case-by-case basis. All right, so we're going to try a couple more of those so we can do some of the rational function ones. So let's take a look at this one, for example 2. So you have a rational function. It's a ratio of two polynomials. We want to look at the limit as x approaches 2. So we're actually going to see what we can do with direct substitution. Then we're going to take a peek at the graph. So this function, when I look at the domain of this rational function, so I'm going to start with that. The domain, we worry about if it's a rational function ratio. Remember that the denominator can't be 0. So what makes the denominator 0 is x equals 0. So that means our domain is all real numbers, and x can't be equal to 0. So I would be worried if I'm asked for the limit at 0 because I don't know exactly what's going on there. But I've asked for the limit at 2. Okay, so theoretically at 2 it should be fine. So let's see if we can do direct substitution. So we'd have 4 minus 2 squared over 2. Well, that would be 4 minus 4 over 2, or 0 over 2, which is just 0. So the limit should be 0. So I should be able to actually evaluate what that is because this function is defined at 2. So if you go ahead and take a second to pause and type that in, or if you have a moment to do it as I'm typing it in here, you can actually evaluate this limit because it is defined there. The place where it's discontinuous is not where we're trying to evaluate that limit. So I'm going to take a peek and show you what that graph looks like here. And then divided by x. And I'm going to go back to my regular window. So zoom 6. All right, so we have a graph that looks like this, and I want to direct your attention to x equals 2. If we look at the graph at x equals 2, it looks like that is just fine. It's approaching the same number from both sides, so it's closing in on that 0. Just to double check to make sure it's not a point discontinuity, I know it's not from my equation, but you can definitely zoom in. You can arrow, you can look in your table, which is super handy, and see that, oh, yep, at x equals 2, it's 0. It's a great way to check your direct substitution. It's defined, it's continuous there. This is definitely going to be a limit that exists, and it's equal to 0. If I asked you, go back to the graph for what the limit was at 0 here, then we would have issues because this part of the graph is growing infinitely large, that part is getting infinitely small. The limit is not going to exist at 0. So that discontinuity, we call those infinite discontinuities when there's an asymptote, we'd be having an issue there. But that's not where I asked you for the limit. I asked at 2, we're good. All right, let's try another one. All right, so we're going to add a few more. So just to make sure we can tell the limits for each of these. So next one, see if you could recognize this function. That's quadratic. It's a parabola. It's continuous. That means the limit exists everywhere. So that means we can just do regular old direct substitution. So the limit would be just directly substitute. And then again, you can graph and take a look and see, but it should be just fine. We have 9 minus 9 plus 7. So the limit would be equal to 7. All right, let's take a look at the next one. So go ahead, pause so you can write down the equation here first. All right, so for this one, it's just a rational function. I got to check my domain, though, just to be sure. So my domain for this one, I would worry about when the denominator is equal to 0. So the denominator is going to be 0 again at x equals 0. So it's going to be all real numbers. X can't be 0. So if I were trying to substitute in a 0 here, direct substitution, I'd be in trouble. But my discontinuity is happening at 0, not 3. So I should be okay. So we have a 3 squared minus 3 times 3 plus 7. So almost the exact same function, but I made it rational. And then over 3. So the limit would be 7 over 3, so 7/3. And again, you can graph and trace and make sure that that seems reasonable when you look at the picture, but there's no discontinuity there. That's why I'm not worried. Okay, so let's take a look at the next one. So we want to make sure we're following through on each one of these here. Let's check the domain for this one. It's a rational function. So again, pause the video if you need to jot down the equation. We got to set the denominator equal to 0 and see what makes the bottom equal to 0. So let's pull out an x. It's a second degree equation. I have a GCF. Set each of those equal to 0. So the two places that I'm worried about are at 0 and -3. So the domain is all reals, x can't be 0, and x can't be -3. So if I was asking you for a limit at either of those spots, we would have to kind of take a pause here and look and see what's happening at the graph. Is it a jump discontinuity? Is it infinite? Is it a point? What's happening? Now, I don't know if you remember from before, but we did some work earlier in the year about figuring out what kinds of asymptotes and things we would have. So I'm going to have you just take a look. If I factor that denominator, I can actually reduce out that factor of x plus 3. So this function is really just like 1 over x when you look at the graph. So we're going to graph that in a second. So if it's just 1 over x, that means the removable discontinuity was happening here. I don't know if you remember that terminology, but we talked about that earlier. So this is a removable discontinuity, which means it's a point discontinuity. The one that we can't remove, this one, is going to be an infinite discontinuity. So we can't get rid of that one. Infinite discontinuity means that there's an asymptote on the graph at that location. So we'll take a peek at that. A point discontinuity means that there's going to be a hole on your graph at that location. All right, but the question was, can I do the limit as x approaches +3? Well, how do you feel about +3? It's in the domain of the function, so we should be just fine to do that direct substitution. Direct substitution limits are the easiest ones we can do because it's just substituting the value into the function, because the value of the limit equals the value of the function. All right, so it looks like we have 9 over 18, or a limit of oh, sorry, not 9, 3 plus 3, I can do arithmetic, 1/3, sorry about that. So the limit would be 1/3. So let's take a peek at that graph. So go ahead and pause the video for a second, type that one in. All right, so take a look at the graph here. So it does look like 1 over x. That's that whole removable discontinuity idea. You will see the vertical asymptote at 0, that is not removable. At -3, I know it's super hard, you can't really see it, but there is a whole discontinuity there. And the way I can show that is if I go to my table and I look at -3, or if I zoom in the pixels, there's actually a break. But if I go to -3, it says error. I have 2 places where it's discontinuous. But what I want you to look at is what's happening at 3. So here's 3 on the graph, that's the point. So it's getting closer and closer to that value there, closer and closer there, and it is defined there. There is a point where it's getting closer and closer to this 1/3. So if you go back to the graph, we see that it's closing in on that value. If you go to your table, look what happens at 1/3, or at 3. It's 1/3. 0.3 repeating is how you see it in the table. So because it's continuous there, the value of the function exists. All right, so we talked about this idea of direct substitution. We can do operations with limits when they exist. Being able to recognize the equation and do its domain is critical to be able to figure out what those limits are going to be. So direct substitution, they work pretty well. You can just plug them in. So most of these that you're going to be seeing today are going to be just direct substitution, right? You're going to be able to just substitute the value in because the value of the limit is equal to the value of the function. You're going to have one piecewise graph, number 23, so you're going to want to graph it first to see what's happening at 2. And then I'm just going to scooch this on down for the last ones. For 70, you're checking out and answering questions about a graph, just like the first one we did today. And then 71 and 72 are going to ask you some questions about, hey, what did they do wrong? What error are they making in their thinking? So for today, the big idea is direct substitution. It's all about continuity.